I'm Karen. This is Helena. That's Diane on her way up. Our goal today is to give you an idea of what things can be done with Geode's WAN distribution feature. There's an awful lot to cover, and we're going to push the time limit here. So here we go. This presentation contains 3 parts. We're going to introduce the WAN distribution feature, the problems it helps to solve, and how it works. Then we'll describe how you can apply the feature in ways that solve real issues. Last, Diane is going to work through, in a virtual way, we hope, the Geode example that demonstrates an active-active system. First part of the talk motivates WAN distribution and explains how it works. 2 issues that we face are fault tolerance and performance, meaning maintaining the speed of our system. Let's discuss both. We commonly use redundant copies of our data as a way to recover from or tolerate failures. I assume you already know about Geode's ability to use redundancy within a cluster to tolerate the failure of servers without data loss. For this talk, I'm actually talking about failures of entire data centers, in which we face the failure of an entire Geode cluster. We'll cover the blue-green disaster recovery pattern, which uses WAN distribution to implement a hot spare, increasing fault tolerance. With data that is generated and needed around the world, we face the challenge of latency in global data propagation. Since updates within a cluster are synchronous, placing servers within a single cluster at globally distant locations would introduce unacceptable delays. Geode's goal is a design in which we maintain and maximize the performance within a cluster while allowing the global hosting of regions. Let's talk about the implementation of Geode's WAN distribution feature. This feature allows distinct clusters to host the same region. Updates and writes to the region are propagated asynchronously from one cluster to another, allowing the receiving cluster to eventually become consistent. The updates are asynchronous for performance reasons. It allows region operations on the cluster where the operation originated to continue without waiting for a globally distant cluster to receive and acknowledge receipt of individual region entry updates. The implementation uses queues to batch up sending updates from one cluster to another. On the sending side, we have a gateway sender. In implementation, it's an asynchronous event queue. Region update and put operations and queue those operations in the gateway sender. Batch sends propagate the events to the receiving cluster site where there is a gateway receiver, which acknowledges the receipt of the batch and updates its region. Here's some quick implementation details you want to know. Each cluster is assigned a distributed system ID or DSID in our diagrams. There will be one gateway receiver per server. Each gateway sender gets paired with a remote cluster by specifying the remote cluster's distributed system ID. And under most circumstances, you will configure a distinct gateway sender for each region. For our advanced users, yes, you can have a single gateway sender for 2 regions if the regions are co-located. For the remainder of this presentation, we're using simplified diagrams that show the gateway sender and gateway receiver as if they were one component. And I wanted to note that data can be propagated unidirectionally from one cluster to another, or we can configure 2 unidirectional queues to implement a bidirectional system. We'll cover configuration in the example demonstration. You'll see this soon. Okay, those are the basics of how WAN distribution works. Now let's use this to see how the feature implements interesting design patterns. The blue-green disaster recovery pattern specifically addresses the need for fault tolerance at the level of cluster failure. It implements a redundant copy that acts as a hot spare. That hot spare is a passive cluster. And in case you have not heard the terminology before, the cluster description of active means that the cluster does updates or writes to region data. And for our purposes of talking about WAN distribution, it implies that there is a gateway sender configured for the region. A passive cluster is one that makes updates that arrive through its gateway receiver. One more note, there's also a design pattern by the name blue-green, which addresses the need to deploy new versions of software without any downtime. We don't have time to cover that pattern today, but yes, you can use Geode's WAN distribution feature to implement a blue-green code deployment. For the blue-green disaster recovery pattern, assume that the initial state of the system has blue as the active side and green as the passive side. Region operations are all directed at the active cluster. All put and update operations are propagated to the passive cluster via the gateway sender. The common implementation sets up a bidirectional propagation, but nothing flows from the passive side to the active side because no region operations originate on the passive side. The redundant copy, again, is a hot spare. So when the disaster occurs, the active cluster becomes unavailable. Monitoring of the cluster that's outside of Geode notices the failure, and the passive cluster takes over by being promoted to be the active cluster. You might have noticed the purple dot in the gateway sender. It represents data that didn't get sent before the active cluster failed. Unless the gateway sender is configured to be persistent, that purple dot represents data loss. An external load balancer is going to redirect all applications to the promoted and now active green cluster. That load balancer, also not part of Geode. The typical design assumes that the missing site will return shortly. So we'll assume that blue will be back and it will become the new passive cluster. That was me? Okay. Okay. Blue is back as the passive cluster. If the sender queue on cluster A was configured with persistence, any data left in that queue would now get delivered to site B, and the conflict resolver would determine if the data event needs to be applied. And we alternate between blue and green as the active site as dictated by the changing environmental conditions. Here's Helena to describe our next design pattern.
Active-active is one of the most commonly used high availability WAN topologies. This configuration allows for multiple sites to be actively used to read and update data. A Geode deployment configured for active-active consists of 2 or more data centers running Geode clusters. The sites communicate with each other by means of bidirectional WAN gateways. In this diagram, we have 2 sites, A and B, connected over WAN. They each have gateway senders that queue changes to be sent to the other site. The apps, also commonly called clients, perform gets and puts at both sites. There are other components in these configurations, such as an external load balancer, but we will be omitting those for the sake of simplicity. Another component of this topology that will not be pictured in the following example is the gateway conflict resolver. Since both of the sites are being actively used to update the data, conflicts may occur. The conflict resolver is responsible for ensuring that all sites have a consistent view of the data. When 2 or more sites try to change the same entry at the same time, the conflict resolver decides which change to apply. In order for the conflict resolver to ensure consistency across all of the sites must have the same conflict resolver. In Geode, by default, there is no implementation of the gateway conflict resolver. Instead, conflicts are resolved by using version vectors and, in the case of a tie, system clocks. Note that this means that all site system clocks must be synchronized. This behavior can, of course, be overridden to provide a custom method of conflict resolution for your Geode cluster. So in this simple example of a Geode deployment, we have two sites, one in New York and one in London, each hosting a region of products that will be actively queried and updated at both sites. They are connected using the bidirectional WAN gateways and each have apps connected to them. In New York, one of the clients puts a new entry, which is a shirt that costs $15. The data gets stored in the region in New York, and that operation is immediately added to the queue to be sent to the other site. When the London site receives that operation, the conflict resolver checks that applying the operation will not conflict with the current data at the London site and then puts the new entry. So now we have data consistency across all the sites. So now the London site has started a sale and the shirt that used to cost $15 is now $10.50. That operation is first stored only at the London site, which makes the two copies of that data inconsistent. But the operation is also added to the gateway sender, and the New York site will, did I get there? Nope, there we go, okay. And the New York site will receive and apply that change in the same way as the London site did, making the two copies of the data consistent again. So there is a brief amount of time where a client at the New York site may query for that product and get back the incorrect price, but the data is quickly updated. Fine-tuning of the configuration can help reduce this latency, but WAN bandwidth is still a limiting factor. So active-active may also be used with multiple regions. For instance, we could have a region of products and one of customers. Each of the regions will have its own gateway sender, and each of the servers will have a gateway receiver. When the gateway receiver receives an operation, it is applied only to the relevant region. The active-active pattern can also be paired with a blue-green disaster recovery pattern. With this, one site is the active site for a region while the other acts as a backup. In this example, the New York site would act as the primary site for the New York products region while acting as a backup for the London products region. An external load balancer could be configured to promote a site to be active for both regions if one of them were to go down. Active-active allows for multiple sites to be serving clients the same data simultaneously. The data at each site will eventually be consistent once all of the operations have been sent to all sites and conflicts have been resolved by the gateway conflict resolver. With active-active, reads end up being faster than writes because writes must be sent to all sites and may have to sit in a queue before being sent over WAN, whereas reads can be performed just one time at the most conveniently located site. So now I'm going to move on to talk about another pattern. Command query responsibility segregation, or CQRS, uses different models for updating the data than for reading the data. CQRS enforces a separation between queries and commands, where commands are only allowed to modify data and queries are only allowed to read data. Queries must be able to be replaced with their results and have the same meaning, so they must not have side effects. CQRS makes it easier to reason about the state of a system, but does introduce some complexity to the implementation, especially for concurrent systems like Geode. For Geode, in the simplest case, CQRS means that one site would be responsible for updating the data for one or more regions, and one site would be responsible for reading it. So here, when data is updated at site A, the gateway sender sends a message to site B to make the same update. The change would then be available for read at site B. This separation of responsibility does introduce some complexity, but provides the benefit that queries can be ran at any time on site B without risk to the data since they have no side effects. Note that the WAN configuration here looks similar to that of the blue-green disaster recovery pattern using the unidirectional gateway senders. The primary difference between these two patterns is, first of all, the restriction on the apps accessing each site, and that the two sites' responsibilities will not switch in the case of a disaster without additional configuration. So here's an example of where a CQRS pattern might be useful. We have two sites running Geode clusters. One, Site A, is a factory floor where cans of coffee are being produced. Site B is an analytics site where the data from the factory site is being queried and analyzed. In this example, Site A is responsible for commands and Site B for queries. Data is going to flow in only one direction from Site A to Site B. If we introduce a second region, for example, if the factory starts producing coffee with milk in it as well, the same principle from the previous example holds, but with each region having their own gateway sender for changes to data in that region. And now, back to Karen for the hub and spoke pattern.
Thanks. In this, let's go back one. There we go. In this pattern, which is really a topology and not a design pattern, there's a central cluster, which is the hub. The hub communicates with each of the surrounding clusters, which are the spokes. This topology reduces the quantity of connections as compared with a fully connected mesh. But as all communication goes through the hub then becomes a single point of failure and perhaps a bottleneck. If we're sizing our system right, this shouldn't be a problem. This topology is frequently combined with other patterns. One common design connects the hub to a passive cluster, which again acts as a hot spare. With this topology, we can create a variety of design patterns based on whether the spokes are active or passive. One common aspect to all of these designs is that they operate on data in ways that are specific to a cluster's location. That is, the patterns are location aware. For example, we could choose to connect a running application to the cluster that is physically close. This should increase performance over connecting to a physically distant cluster. We could write only to region entries at a particular site as if a particular cluster owned a portion of the region entries. We'd preface all write or update operations on location such that only the owning cluster writes to data, while the other sites can passively read or be redundant copies. In this way, all spokes can host the same region, but there will be no conflicts. Operations originating from a site in another part of the world could be sent to the hub and then forwarded to the right site based on physical location. A nice way to accomplish this is to deploy a gateway event filter implementation on the hub. The filter's before enqueue method is called synchronously before the event is enqueued in the gateway sender. The filter's Boolean return value determines if the event is enqueued or not, so the before enqueue's implementation identifies which clusters will receive the event. A variation on a hub and spoke topology is the follow the sun or global book pattern that is used by financial services. For those financial services, transactions need to take place within an active time zone, and that time zone moves over the course of a day. So wherever an operation originates, it is forwarded to the cluster within the active time zone. The cluster in the active time zone is the hub. In implementation, we fully connect the sites, assuming that each and every site will at some point become the hub. Then we introduce a token that identifies the hub or active time zone, and at appropriate times, pass the token from exchange or site to site around the world. In this diagram, the New York cluster is the hub and has the token. All orders are forwarded to New York for processing. The token is passed at the appropriate time, as here, where the Tokyo Exchange is now the hub and processes all the orders. Okay, it is now time to see WAN distribution in action with a demo. Diane.
put this up one?
I don't know.
What I don't know, am I mic'd? You guys hear me? No. You can hear me. Oh, now you can hear me. Do I hit this in it? Okay, so this is the slide. What I don't know is supposed to be able to start a video. And if it works, it's gonna be great. Did you want me to try the volume on this now? Hello, this is Diane Hardman, and I'm a product manager here at Pivotal and a contributor to Apache Geode. Today I want to walk you through an example of how to set up 2 Geode clusters to share data using WAN replication in a bidirectional active-active configuration. This features a great way to keep 2 data centers updated with changes made at either site, and the options that are needed to add to the cluster startup script are really quite simple. The code for this demo can be downloaded from the Apache GitHub repository for Geode examples. The example is currently on the develop branch, but will soon be released with Geode 1.7. The original WAN example creates 2 clusters on your local machine. For this demonstration, however, I've modified the scripts to create the clusters on 2 different machines. We'll refer to one cluster as the London cluster and the other as the New York cluster. Each cluster will contain an example region configured to use the gateway sender directing data events to the other site. Finally, I'll run a simple client application that connects to the London cluster and puts 10 entries into the region. We'll then verify that both sites contain all the entries. Let's run the example and take a look at the scripts. The terminal on the left is connected to my MacBook and will represent the London site. The terminal on the right is logged into a Linux box in the other room and will represent the New York site. I'm going to start the scripts in both terminals, and then we can examine the contents of the script in another screen. This is the script that is run for starting up the London cluster, and it contains 1 locator and 2 servers. But let's focus on the options for configuring the WAN. These are standard start locator options, but there's 2 specific ones that need to be added for WAN replication. The first is the remote locators property. This property is used to identify the IP address and the port that the remote site locator is using. This will allow us, the locators, to communicate with each other about what servers are available in each cluster and what regions are loaded on those servers. The other important property to configure for the locator is the Distributed System ID, or DSID. Each cluster must have a unique integer assigned to it for a Distributed System ID. For the servers, the same Distributed System ID needs to be specified so that we know this server belongs to the London cluster. In addition, one other property to set for the servers is to set conserve sockets to false. This allows the maximum communication for WAN replication and to make sure we have the best throughput. After both the servers are started, it's time to create gateway receivers. The create gateway receiver command will configure receivers on all servers in the cluster. It's important to note that you can only have 1 receiver on each server. Next, we would configure gateway sender. In this case, the options represent where the sender is sending data to. So we specify a string ID, and typically the string will be the name of the remote site we're planning to send updates to. It's also important to identify the remote distributed system ID. In this case, for the London cluster, we need to be communicating to the New York cluster. So the New York's DSID is 1. Finally, we could specify whether we want parallel or serial gateway senders. For most regions, especially partitioned regions, you probably want to set this to true. And in fact, that's the default if you don't specify anything. When you have parallel gateway senders, all servers containing data for that region can be sending data across the WAN, which will maximize throughput. You would only configure serial gateway sender if you had a replicated region, or in the case of a partitioned region, if you needed to preserve the order of events across different keys in the region. Now that we've got the servers up and running, let's go back and run the command that will add the region. I'm going to run this next script that will connect to each site and add the region. What's important to note as the create region command in this script, as it connects to each cluster, the create region command is pretty standard. You specify the name of the region, the type of region, in this case a partitioned redundant region, but the additional option required for WAN is to specify the gateway sender ID. In this case, we're connected to the London cluster, and so by adding this example region, we're saying use the sender that's going to target any data updates to New York. Now that we have both clusters set up with their regions, let's run the client application that will connect to the London cluster and add 10 entries. I've already built this client application. It's really quite simple. As it adds the entries, it'll print them to the screen. So here's the key and value for the 10 entries that this client application added to the London cluster. So let's now connect to the cluster and make sure that those entries are actually reside in the region. I'm using gfish and will now connect to the local London cluster that I created earlier. And let's list the members to make sure that we're in the right site. Yeah, we're connected to the London cluster. Let's do the same over on the New York site. Again, I'm on a Linux box over here. Geode 1A. And indeed, we can see that I'm connected to the cluster on the New York side. Now let me verify that those entries got added to the region by querying the region. As you note, the OQL syntax is very similar to SQL. And there indeed are the entries in the example region on the London side. But what's more important is let's see if those got replicated over to the New York side. And indeed, we see that now the New York site has the same regions that were put into the client, from the client into the London site. But just to make sure we've got bidirectional set up, let's put an additional value or additional entry into the region from the New York side. Okay, we'll run our query again to make sure that it got there. Sure enough, it was put on this region, but now let's see if it got replicated back to the London side. Indeed, it got replicated back because there's value 25 over on the London site. So this completes the demonstration of bidirectional active-active WAN replication. Please download this example from GitHub and play with it on your own machine, as well as any of the other Geode examples. Thanks for watching. Yay, we're done. It's not letting me go to the next. There we go. So We're all up here to answer questions. I do want to respect the time. There's one more speaker today. Oh, we still have 5 minutes. Cool. So does anybody have questions about WAN replication? No. Yep. All your questions answered. Yes.
If you're handling transactions, you're doing updates to multiple regions that need to be consistent, so you don't get inconsistent on the other side. What's the best approach for handling that?
With WAN replication, I should look at Anthony. I know you have to, with the WAN, with the transactions, you have to have your regions co-located.
Yes.
I think, again, if you've got them using the same gateway sender, I think because they're co-located, you can have them send through the same gateway sender. I think that will work. And Anthony, can you confirm that?
Are you asking for transactions across clusters?
You can't do that.
So an update, say you have several updates and you apply across a few different regions, and you want to replicate it to the remote side.
Right.
So you might use a serial gateway, possibly the serial gateways for the regions together, right? So is there a way to wrap that in transactions somehow without writing a lot of code to validate that the remote side receives all the updates to have a consistent transaction across?
I believe you're asking for transactions that are distributed across the
No, I think
WAN
let me see if I
gateway.
can repeat the question. You can correct me if I've not repeated it correctly. You're doing transactions that involve components across multiple partitioned regions. If you're doing a transaction with partitioned regions, the buckets need to be co-located. So you've already configured them to be co-located if your transaction crosses region boundaries. Whether you use a parallel gateway sender or serial gateway sender, as long as they are co-located, you should be able to use the same gateway sender to send those updates. But I should probably get your name and follow up and confirm that later. I believe that to be true, but I'm going to get confirmation from some other folks on that. Did I state the question correctly? If you're using partitioned regions, your region is partitioned, it's broken up into buckets, and those buckets get distributed across the various servers. So each region would distribute its buckets one particular way. If you need to do a transaction, means across two regions, you need to guarantee that the way their buckets are distributed line up. And I'm sorry, what? Partition resolver is the word. You do write a partition resolver to make sure that they get lined up so that bucket 1 for region 1 and bucket 1 of region 2 are co-located. So once within a cluster, you've got that co-location set up for your transaction. The transaction's happening on that cluster, and you're saying you want that transaction then to get replicated off to a different cluster. Is that right? You're not trying to do a transaction across clusters. You just want the one transaction happening in one cluster. Yes, yes, as long as you're not trying to implement the transaction, saying I want part of the transaction done on one cluster and another. I don't think you're saying that. You're just saying whatever happened on this cluster, I want it copied over to another cluster. Yeah, we can do that. I'm hoping I answered your question. If not, let's follow up afterwards, okay? Are there any other questions? Yeah.
We're saying that you're picking cluster, the thing replicated using some kind of queue technology.
Yep.
Right?
Yep.
Can I know what is the underlying technology that is being used to queue that up? And is that persistent? And do we have any options around social media?
Yes. So the question was, with WAN replication, we're using an underlying queuing technology. You're kind of interested, what is that queuing technology? And is it possible to persist it? Did I get that right? Yes. Yeah, in fact, the way the WAN gateways are implemented uses the same technology as an asynchronous event queue that's a core part of Geode. And it has a lot of stuff built around that to handle WAN, but it's essentially using an async event queue. And one of the options, I didn't show it in the example, when you're setting up the gateway sender, is you can give the option to persist it. And I think Karen talked about the situation where
you have your whole site go down. There was things left in that queue that didn't get delivered to the remote site. If the queue is persisted, when that initial site comes back up, it says, oh, look, there's an event there, and it does get sent. If you didn't persist your sender queue, then that data's gone. Does that make sense?
Right. My question was that asynchronous event queue is Geode-based. Can I use like
Yes.
something like Kafka or APACHE or something?
Oh, to use Kafka? I don't know that I have the answer to that, but maybe I can find out and get back to you on it.
Thank you.
Okay. Any other questions? If not, I know we have one more speaker. Right. Thank you, guys.